Right, but we did cover single, double, and triple bonds, right? Okay, so we're going to talk about Lewis structures again. And we're going to kind of go through the process for drawing them, and then we'll cover lab, and you guys get to practice on lab drawing them. You can practice on the homework drawing them. And then what we'll do is on Wednesday's lecture, we'll talk about how the geometry of them, what shapes it does, and then that concept of polar molecules versus nonpolar molecules. And so you can do half the lab today, and you'll do half the lab on Thursday, kind of, and some of it in between maybe even. So as a review real quick, what are valence electrons? Yeah, they're the highest S&P electrons, right? I mean, there's a lot of different ways to say it. Let me know. I can write bigger. I forgot we're in the other classroom. Okay, so we've got our valence electrons. How do we determine the valence electrons? For instance, you know, oxygen has how many valence electrons? We count over the columns, right? It's in column 6. Therefore, it has 6 valence electrons. And so we can draw them like this. 1, 2, 3, 4, 5, 6. Now, if sulfur's in the same row, what do we know about sulfur? It also has 6 valence electrons. So what's the same in each column is the number of valence electrons. So each column, nope, has the same number of valence electrons. Not because it's necessarily -2, but it's a -2 charge generally because it wants to gain 2 more electrons. And so to complete its octet, it would gain 2 electrons and have a -2 charge. Let's see. That just blew my train of thought. What was the next thing we wanted to review real quick? So we kind of know where to get the valence electrons from. Oh yeah, that octet rule. What does the octet rule say? Yeah, elements, all elements, except hydrogen, want 8 electrons in their outer orbital. That this is very stable. And of course, hydrogen is the exception to the rule because hydrogen just has a 1s2, meaning it's happy with just 2. Because it doesn't have, there's no such thing as a 1p orbital. And so because there's no 1p orbital, well, that's when it's happy, right? When it has 2, meaning it's happy with 1s2, meaning the octet rule, right, a filled orbital for hydrogen is 2 electrons. A filled S&P orbitals for every other element is 8 electrons. So remember, count to 8, except for hydrogen, count to 2. Right, the highest S&P quantum numbers. So we've kind of got our basics for how to figure out the Lewis dots for each individual atom. And what we should recognize then is that atoms follow patterns because of our rules for having an octet. For instance, if I take a look at the halogens, that's fluorine, chlorine, bromine, and iodine, they have 7 valence electrons, and so they look like this. So how many electrons do they need to get to share? They need 1 electron to have an octet. I'm just going to say 8 because I'm tired of writing the word octet. Therefore, they form 1 bond. Now, these rules can all be broken, but not in this class. At least, hopefully not in this class. Meaning there are always violations to the octet rules, especially when we have elements that begin to have d orbitals, but we're going to ignore the violations to the octet rule, hopefully. So halogens always need to have 1 bond. What about if we look at oxygen, sulfur, and tellurium? We know that they have 6 valence electrons. So, right, oxygen tends to form 2 bonds. Now, that could be 2 separate bonds, or it could be 1 double bond to the same element, meaning we could have oxygen that looks like this, where it's sharing to 2 other elements. And I'll just put X's down because we don't care what element it is. Or you can find oxygen that looks like this, that has 2 single bonds to stuff. Oh, I'm sorry, I actually drew that. That's the one I just drew. So here, it has a double bond to 1 atom. So that's how we're going to tend to find oxygen when we're drawing structures. Occasionally, you'll find oxygen with 3 sets of lone pairs and a bond to something. But this is going to be, hopefully, I think this is rare in our class. I should double check to make sure I didn't include any of those. So the idea is that we can start finding patterns based on the number of valence electrons things have. The nitrogen and the phosphorus family have 5 electrons that are valence, and so they look like this. So how many bonds does nitrogen have to form to be happy? It has to form 3. And so the idea is that I can have nitrogen with 3 separate bonds, or I can have nitrogen with a double bond and a single bond, or I can have nitrogen with a triple bond to something, as long as it's bonded to 3 different things. And then, of course, the exception to that is in ions, it's allowed to have 4. So for instance, if I take a look at nitrogen in the ammonia molecule, we're going to find that it forms that's our normal cation. It's allowed to have 4. So, we can break these rules. It's just for normal molecules, we're not going to break it. The only time we're really allowed to break those rules is if we have extra electrons or we're missing some electrons. Let's see, what's after nitrogen? I guess really then hydrogen's one. Hydrogen always makes 1 bond. It's impossible to find hydrogen with more than 1 bond, so it's always going to be bonded to something like that. So recognize that you've only got a limited number of tools in your toolbox. You've only got a limited number of structures that each of these elements can form. And so once you pick up on these patterns, once you've practiced enough of these Lewis structures, they really do start to become second nature, and I think you'll be okay with them. But it does take a little bit of practice, and especially at the beginning, it takes a little bit of trial and error until you pick up on those patterns. So be willing to try something and be wrong, and then realize if you're wrong, just start over and try something different. One of the rules for Lewis structures is step 3 is to simply trial and error. It really is to a certain extent. Now, you can have good trials by kind of understanding the rules and not make as many errors, or you can just kind of randomly try a bunch of different things until you find one that works. Okay, so how to make more complex Lewis structures. So the ones we looked at before were very easy, meaning for a little bit of review, and hopefully, I know it's not enough to totally understand, but at least Cody will have the parts and the terminology down maybe since she was gone, is we took a look at, for instance, if we have chlorine, we know it makes a single bond, and everyone has 8 electrons around it. But then for oxygen, we found that it formed a double bond, right? Meaning it had to share more sets of electrons. And nitrogen had to form a triple bond in order to be satisfied. And we know that, Cl2 exists, we know O2 exists, and we know N2 exists. So we know these types of things are possible. And so what we're going to find is that when we run out of electrons, when we don't have enough electrons to make everyone happy, we're going to make double and triple bonds. So we've got that terminology. And so what I mean by more complex Lewis structures is simply molecules that have more than 2 atoms. Notice all these have just 2 atoms, right? They're not too hard. So we're talking about maybe things with 3 or 4 atoms in it, and they're going to get harder. So the rules are in your handout. And I have to be honest, I number them different every year, mostly because my numbering is somewhat random. So realize that if I say rule number 3 and you look on your paper and it's actually rule number 4, it just means I stuck 2 rules together. So the very first rule we have to do is add up valence electrons. Because remember, valence electrons are the ones that are responsible for the bonds. Yep. And so we have to count the valence electrons up. And then also remember that if I have an anion, they have extra electrons. And of course, cations are missing electrons, and so they have not extra but less electrons. And what I'm going to do is I'm going to put each rule up, and then we're going to do 3 example molecules for each rule. So my first example molecule is simply going to be CH4. So how many valence electrons are there for CH4? Well, which column is carbon in? Yeah, carbon has 4. Hydrogen has 1. And how many hydrogens do I have? 4. And so 4 plus 4 is 8 electrons. And then we can do NH4 plus. Nitrogen is in the 5th column. Hydrogen is the same. 4, and each one has 1. So that's 9. But what does that little plus mean? Yeah, minus 1, because I'm missing, or I essentially lost, electrons. So this is really 9 minus 1 is 8 electrons again. And then a slightly harder one, CO3 2 minus. Well, carbon has 4 valence electrons. How many does oxygen have? 6. And I've got how many oxygens? 3. And then what does that mean? No, the minus 2 means I have extra, so that means I have plus 2 more electrons from that charge. And so 4 plus 18 plus 2 is, let's see, I'm doing in my head 18, 19, 20, 24 electrons. Now I have to admit, I said that, you know, if you can count to 8, you're pretty good, and that you have to take your shoes off, that's okay. I admit 24 is a bit of a big number, and you might have to borrow a friend's fingers to count on. But I think it's doable, right? Is everyone okay with the math? Okay, so one of the things that you should realize is that this is an easy step to skip. I have no idea why, but the first thing I start seeing people doing is just drawing things instead of following the steps. This step is crucial. You can't tell if you've got the structure right or wrong unless the electrons add up to 24 or 8, depending upon which one you're drawing here. Meaning you can draw lots of Lewis structures, but if you draw a Lewis structure with 22 electrons and there's really supposed to be 24, it's wrong, just plain and simple. So you got to be able to do the math part right. Okay, step 2 is what I consider kind of the tricky step. It's the one that causes most people frustration to start with, which is why I tell you, be okay with getting it wrong. And that's you have to write a trial structure. Yes.
So what happens if we take, for example, cobalt?
Cobalt?
Yeah.
We don't. That's the whole point. We don't allow things with d electrons. Cobalt has d electrons, right?
Well, so does iron.
So does what? Do we use hydrogen in this lab?
Oh, never mind.
Yeah, see, we're not using d orbitals at all. So just be happy. S and p orbitals. We're ignoring all the d electrons. We might, if we're bored and finish lecture 15 minutes early someday, talk about exceptions to the octet rule, but probably not.
Not that I'm complaining.
I know.
But
I'm saying we're trying to keep it as not as simple as humanly possible, but as simple as reasonably possible. Once we get to d orbitals, it becomes much more confusing. So.
We had that bromine minus on the formula. So we just ignore the old ED that's in there?
Exactly. We ignore the d electrons.
So we're just looking at S and 5 P.
Yeah, because those are the highest numbered orbitals, the 4 is. So we can ignore the electrons in the d orbitals. Just ignore d orbitals because they're closer in than the 4p. Okay, so we want to write a trial structure. There's some general rules for writing trial structures. These rules are not 100%. And as much as I try to make sure all the examples follow them, sometimes one might slip that doesn't. So in general, we want a symmetrical structure when possible. Now, sometimes it's just not possible to be symmetrical. And in that case, you know, you're not going to have a symmetrical structure. For an example, you know, if I take a look at CO3 2-, well, the most symmetrical way is to stick carbon in the middle and put 3 oxygens around it, right? As opposed to going COOO or OCOO. Oops, I guess I need a dash there. And so, you know, this is our proper trial structure for when we start that one. The other ones are too easy to bother with. But the idea is symmetrical as possible. Now, again, if you can't make a structure symmetrical, meaning there's just an odd number of atoms or something strange like that, then you can't have a symmetrical structure and you've got to come up with something else. We generally put the least electronegative element in the middle. Again, probably true 90% of the time. There's some cases where the least electronegative element won't be in the middle. Hydrogen plus the halogens are never in the middle. Mostly because, remember, they can only form one bond. And so you can't really stick hydrogen or a halogen in the middle and have it only form one bond because it's not really in the middle then. Then oxygen rarely, and in this class never, forms oxygen-oxygen bonds. So for instance, the other thing is we get rid of both of those trial structures because we never expect oxygen to bond to itself. There's one exception to that that's common, that's hydrogen peroxide. Most people are familiar with that. After that, oxygen just would rather bond to other elements than to itself. So those are some general rules that we want to find. So if I'm drawing the general, following the general rules for these molecules, if I look at CH4, what element has to go in the middle? And then if I want to make it symmetrical, then all of the hydrogens go around that carbon, right? So there's our trial structure. Now, does that mean you, and see, it totally violates our rule if I do something like this. Because quite honestly, I'm not allowed to have a hydrogen with 2 bonds, right? This hydrogen has 2 bonds, not allowed. And if I take a look at NH4 with a plus sign on it, again, the most logical structure is the nitrogen with 4 bonds to hydrogen. And we also already kind of looked at CO3 2-. We expect carbon to have the oxygen symmetrically placed around it.
So what does the charge do to the structure?
Nothing yet. Well, okay, it's done one thing already, technically, right? It added 2 extra electrons to when we're keeping track of them, right? So, you know, this had 8 electrons. This had 8 electrons because it was missing one. It normally would have 9 if we counted them. And this has 24 electrons. But if we just counted it normally and ignored the 2-, it would have only had 22. So for now, the extra electrons don't do anything other than affect the number of valence electrons. Okay, so step 2 is the tough one. Step 2, I think, is the hardest step, just getting started. So be willing to just put something down on paper and try it. And if that doesn't work, be willing to say, okay, I'm going to put an X through it, and I'm going to try something else to see if it works. Okay, step 3 is some more math. So valence, electron, math. So the idea is that we want to subtract 2 electrons from our total for each bond. Because remember, that line is the same as 2 electrons being shared, right? And so, for instance, if I take a look at CH4, oops, I start with 8 electrons, right? And then I use 8 electrons in bonds. And so how many electrons am I left with? And then same thing with NH4. I need to find a better example of a positive cation. There's just honestly not very many positive examples anyway. Same thing, I start with 8 electrons, I use 8 electrons, and I have 0 left. What was that, Jay? Yes, I will slow down a little. Take a break, check to see who called me because I'm bored. And normally people don't call me during my class. Oops, I don't really care who it is. Oh, Countryside Vet called me. That actually might be important because I need to get my horse a Coggins test so that I can sell her.
You're selling your horse?
Yep, I'm going to get her a different horse. What? That's kind of like trading in a girlfriend for a new one. Depends on how nice of a horse you want. My last horse was free.
Free? You just got a free horse?
Was a Christmas present.
Oh, what? Nice Christmas.
It is. Okay.
Sell it.
Okay, so if we take a look at CO3 minus, I started with 24 electrons. I've only used 8. I'm sorry, 6 in this case. Whoops. And so I have 18 electrons left. So what I'm doing is I'm counting the electrons in the bond. So that equals 2 electrons, 2 electrons, etc. So since I made 3 bonds, that's 6 electrons that I've used up already in my picture. And so I've only got 18 left.
And the start is the first step when we were counting.
Right. So our first step was simply to count all the electrons and then draw a trial structure. And now we start getting rid of the electrons and adding them to the trial structure.
And the lines equal to?
2. Because that's what the line is representing, 2 electrons being shared between the atoms. Okay, so step 4 is to complete octets. Or to check that they're all completed. So for instance, if I take a look at this, what I'm saying is check and make sure every atom is happy. For instance, that hydrogen has 2 electrons, right? So it's happy. And all the other hydrogens look like it. And if I look at carbon and count the shared electrons, carbon has 8 electrons and it's happy. If everyone's happy, we are done. I know, that's why I'll slow down. I forget you guys don't have as elite drawing skills as I have yet.
Well, really what it is that you're really great at talking and writing at the same time. Nobody else can do that.
It is a talent.
It is.
It took me a long number of years to figure it out. I used to not be able to talk and write at the same time.
Did you stop sub-vocalizing when you write?
I don't know. Now you confuse me. Now I'm not going to be able to write and
Well,
talk.
when most people read, they say the word in their head as they read.
Oh,
If
God,
everyone
no.
is happy, you don't say it out loud, but you say it in your head. You don't do that.
No. The hardest
Why
part
do
is
it?
saying something and then writing something different. You'll notice occasionally my letters get mixed up or I'll write something twice. That truly is a talent.
That's because people sub-vocalize.
What I find I can't do is I can't type and talk. It's
Yeah, a
very
lot of people
tough.
can't text. I can text and talk, but I can't write and talk.
Yeah, see, I can't text and talk. Anyway, so in this case, we're all done. And if we take a look at this one also, we can see that we have 2 electrons, and then the nitrogen has its 8 electrons, and so we're done too. But we should remember, if it's an ion, what do we need? We have to put brackets in it. Because if you just count the electrons in NH4, you should have 9 electrons total. But by putting it in brackets and putting that plus sign, we're saying, no, really the whole molecule is missing an electron. And so in order to show things that are ions, either having a positive charge or a negative charge, we have to enclose them in the brackets. And that's just to really let people know that, no, you can't just count the valence electrons. You have to remember you're either missing some or have extra. Alyssa.
So, I don't get the 2 electron part for the hydrogen. Is it that there's 2 electrons for each hydrogen, so then the 8 on the inside equal that?
Well, what we're looking at is each hydrogen separately, meaning this hydrogen has 2 electrons around it because of that shared bond, right? So it's happy. This hydrogen also has 2 electrons between it and the nitrogen, so it's happy. And so really we're looking at each one separately. Yep, you're missing one because that's what a cation is doing. It's missing an electron.
So you have to put the plus sign outside the bracket.
Yes, not inside it.
Not inside. Shift wrong.
Just, well, just saying. Well, we'll get to that in a second. That means, see, a -2 charge means you have 2 extra electrons, right? So yeah, go back and remember what those numbers meant. We're so used to writing Na plus and Cl minus that we kind of forget what the plus and the minus mean, right? It physically means you literally have lost an electron to something else, or you've literally gained an electron from something else.
From something else? What is that something?
Well, in this case, since we're just drawing little fragments, we don't worry about it.
Okay.
But for instance, if we look at the molecule NH4 plus Cl minus, we'd recognize that that lost electron from the ammonia is going to the Cl and the minus. And so when we're drawing fragments like this, we don't tend to worry about where the extra electrons come from.
Okay.
And I'll do CO3 on a separate page. That requires more work. This is our hard example. Okay, so notice, if you remember right, I had 24 electrons to start. I used 8 electrons. And so now I have, I'm sorry, I used 6. I keep getting my examples mixed up. I have 18 electrons left. And what we use those electrons for is to complete octets. So this is rule, see, this is where I lose my numbers, 5, I guess. So what we want to do is we want to complete octets. And our general rule for that is start
We got 5 rules?
with the most electronegative element. Yes, we have 5 rules. So what's more electronegative, oxygen or carbon? Oxygen. And so if I take a look at it, how many more electrons does each of those oxygens need? 6, right? Because each oxygen has 2. Jess?
What does that say?
Start with the most electronegative element first. Well, I asked how many electrons each oxygen needs. So oxygen is the most electronegative. And so what I'm going to do is I'm going to add, say, 6 more electrons to that oxygen, because then this oxygen has 8 electrons. And I have to add 8 more to this, or 6 more, I mean, sorry, to have 8 electrons. So how many have I used so far? Well, I've 16, so I have 6 left, right? So I can put 6 more around this oxygen. And I've got 8 electrons used. So notice that I run out of electrons. So number step 6 is, notice you fill octets, but run out of oxygen, or run out of electrons. So
We might want to do that one again.
So let's look at it this way. I started with 24, right? I used 6 to make bonds. That's those dashes. So then I was left with 18 electrons. And then that's what I'm going to use to do the octets. And now I've used 18 of them. Meaning if I count these little pairs, 2, 4, 6, 8, 10, 12, 14, 16, 18. I count by 2s a lot. Just because 3 times 6 is 18 is tough. But if I go 2, 4, 6, 8, 10, 12, 14, 16, 18, I'm pretty good. So I've used 18 to help complete octets, so now I have 0 electrons left. But the problem is someone's unhappy. I'm guessing there's 8 someones in this class.
What? I'm insanely happy today.
Well, I said 8, right? Not, or did I say 10? I don't remember how many of you are unhappy. 8? So 2 of you are happy. We'll let you 2 figure out who it is.
You know when who called it.
Okay. The rest of you must be just sad and depressed because you don't have enough valence electrons. So notice in this picture, and I'm going to redraw it here real quick just because honestly it's getting a little crowded up there. Normally I don't bother showing the groupings. Who's unhappy in this? Yeah, if we look at carbon, it's only got 6 electrons. So rule 6 is basically if someone's unhappy or if someone has less than 8 valence electrons, share more electrons.
But isn't it CO3 -2?
It is.
But that's counted in the 24.
Right, we already took care of that -2.
So you say, no, bam, we're done.
So the idea is we have to share more electrons. So one of the oxygens has to take 2 of its electrons and share it with carbon to make a double bond, so you get something that looks like this.
Carbon. Yeah, how do we, yeah, it's like, how do we share more of some of those?
Well, notice I took 2 of them from being around the oxygen to not being there anymore. So notice this is missing 2.
Oh, but if it's bonded, double bonded with the carbon.
Right, so that oxygen still gets to count those 2, so it still has 8 electrons, but now the carbon also has 8 electrons and everyone's happy. So the idea is if you run out of electrons, start sharing more electrons. Now there are some rules for sharing. We try to make it symmetrical, meaning if more than one person has to share electrons, you don't take them all from the same person. You take, or the same element, you take it from multiple ones. So that's the general steps for drawing Lewis structures. And I got to be honest, until you start doing it on your own, you won't know if you really understand it. So what I want you to really do is just go ahead and take the lab, set it out, and try to follow the steps. And when you get stuck at a step, feel free to ask a question. But please, at least read through your notes. At least read through the directions on the lab and simply say, okay, Jay, this is the step I'm getting stuck on. It looks like I'm not getting step 3 or step 4. Don't just look at me and go, I don't understand any of it. Because that means what you need to do is read the lab and read the book through. Aaron.
Okay, so the oxygen that double bonded with the carbon, does it still have one more electron?
Have what?
Does it still have one more electron?
Okay, people, we aren't really starting yet. I'm still answering questions. So Aaron, one more time.
Okay, so the oxygen that's double bonded with the carbon,
Right.
does it have one more electron in it?
No.
No?
It had to share both of those pairs, right? So it had to take these 2 to make one line.
So it's not, so it's, the carbon's not sharing one of its electrons with the carbon versus.
Well, it is. I mean, technically one came from carbon and one came from oxygen.
So then wouldn't oxygen have one left then?
No, because remember it only started with 6. So if it shares 2, it should only have 4 that are unshared. Okay, the other thing I want to point out is when you're doing these, if you want, also go ahead and build the molecular models. So that's what these model kits are for. And there's a couple simple rules. Carbon is black and has 4 holes in it because carbon can make 4 bonds. Now, in your model kits, there are some purple ones that have 5 holes that look black. So be careful. If you end up with something with 5 holes, not the right one. Hydrogen is white, and it has 1 hole because it makes 1 bond. Oxygen is red, and it has 2 holes because it makes 2 bonds. And so we assume that it has 2 lone pair sets of electrons on it. For the halogens, chlorine, fluorine, bromine, and iodine, we usually use green with 1 hole. And then nitrogen, in these kits, if I remember right, is technically blue And it technically has 4 holes, but we frequently only use 3 of them.
Can we leave this little chart up on the board?
Yes.
I wanna write about
And then the other thing is to make a double bond, meaning to share more than one set of electrons, use the flexi bonds. For single bonds, use the short rigid ones. And because we're going to do this lab over a period of 2 days, what I'm going to suggest is if you want to build some of the models and then come back and use them the next day, either you'll have to end up rebuilding them because you'll run out of atoms at some point, or if you want to leave a few pre-built, we'll go ahead and we'll leave these in the drawers somewhere.
Okay.
Because one of the things is we're off a day in our lecturing kind of for whatever reason, and we haven't talked about the shapes of atoms. And the shapes of atoms are much easier to see with these models. Now, if you don't want to build any of the models today, don't. Just draw Lewis structures and build the models on Thursday. It's kind of up to you. I'm leaving that as an option. And I think that's it, so let me go ahead and stop this. And then you guys can go ahead and get started on drawing Lewis structures. And what I'll do is if you